I'll be presenting a little bit about the Duracrete and fib Bulletin 34 service life design model code, and also a little addition, AASHTO Guide Specification for service life design of highway bridges. We'll bring that into the conversation as well. So, quick agenda. It's actually quite similar to Mark's presentation. We'll go through a little bit of the history of the development of the methodology that we are presenting. I'll present the actual model. We'll see some equations briefly. And we have to review the design brief. Like we'll take a look at the model cases and just consider the model limitations that we have, and we needed to do some interpretation, similar conversions and so on. So we'll describe some of that. Dig into the model cases, and see what churned out from the model. We'll apply the AASHTO Guide spec and do a bit of a comparison of the model versus what the AASHTO Guide spec says, and then sort of summarize there. So, and that's the Tappan Zee or Mario Cuomo Bridge there in the background. So quickly, history. So, and here I should look at my notes. So, in sort of the 1990s now, wanted to explain a little bit about how the fib Bulletin approach came about, and then also a little bit how it managed to sail across the Atlantic, because it was a sort of a European initial development. So in the late 1980s, 1990s, CEB, which is now FIB, convened a general task group number 20 called Durability and Service Life of Concrete Structures in the 1980s, which released the Durable Concrete Structure Design Guide textbook, basically, in 1995 in a draft state, and then again in 1998. That sort of led right into the Duracrete project. So you see 1996, 1999, the Duracrete project was an EU-funded project including academic and industry partners. And through that process, a framework for a probabilistic-based durability design approach for concrete structures was developed. And the main report from that was released in 2000. That's the same year that the first version of ACI 365.1, the service life prediction state-of-the-art report was released. So building off of the Duracrete project in 2006, the FIB, International Federation for Structural Concrete, Task Group 5.6 developed the fib Bulletin 34, which is called the Model Code for Service Life Design. It's kind of like the Bible from my daily work, let's say. Model code included 4 different durability design solutions or approaches, 3 of which were designed to resist approaches. There's called a full probabilistic approach, partial factor design approach, which is basically LRFD, and deemed to satisfy rules. And then there was a 4th approach, just avoidance. So use stainless steel, for example. The full probability and partial safety factor approaches are reliability-based service life design methodologies for concrete structures, which can be applied for extended service life durations. 100, 120, 200 years have been used in certain places. And like I mentioned, it's a similar concept to LRFD, load resistance factor design. Then in 2012, there was an ISO standard that was developed basically implementing the fib Bulletin 34 approach. Now, fib Bulletin 34 is a framework, actually. Inside of that framework, there's a model. I'm talking about the model today, but keep in mind there's a rational design process described in fib Bulletin 34. Not really getting into that today. It's a different presentation. Okay, now I lost my place. Okay, then how did it travel across the Atlantic? Well, there were some early examples of projects around 2013, I believe. Yeah. The Mario Cuomo Bridge, or the Tappan Zee replacement, as we called it when we were designing it, implemented the fib Bulletin 34 model and service life design approach. And there was a second project running concurrently, the Abraham Lincoln Bridge, which crosses the Ohio River between, I think, Indiana and Kentucky. I wasn't involved in that project. Then, since around 2015, there's been a bit of a process of trying to codify fib Bulletin 34 based approach in North America. So there's been significant focus on development of US-based guidance documents on how to implement service life design on infrastructure projects. The SHARP 2 R19A project was initiated by Federal Highway, AASHTO, and TRB through the second Strategic Highway Research Program. The goal there was to promote service life design concepts through marketing, outreach, and training, various reference materials, including a summary guide on service life design that includes numerous worked examples, different design tools, spreadsheet that you can use to actually do the type of modeling that I'll present today is available on that webpage. It's still available now. Then I need to look at the time here. 2020, the AASHTO Guide Spec was released. So Guide Specification for Service Life Design, I think there's some words there, I think it's of highway bridges maybe added to the end, was released, and that also directly implements the model that's used in fib Bulletin 34, so it's kind of baked into that document. And currently ongoing, and what was just released last year, is the FHWA Service Life Design Reference Guide was published. And that provides a bit of a roadmap for how to implement service life design concepts and methods. It kind of gives information that's useful for owners and designers. Document focuses on North America design practice and on the application of service life design principles for both concrete and steel. Sorry, steel's also there. And note that there's actually going to be some upcoming day-and-a-half-long workshops associated with the FHWA reference guide. And if anybody's interested, reach out to me after the chat. We'll actually be in 2 weeks in Minneapolis for a day-and-a-half-long workshop on that. So, a bit of a background of how we got here. So we'll take a quick look at the actual equation. This is what the model is. It's an analytical equation using Fick's second law of diffusion. That's how it's modeling the process. I'm not going to go through the details, but I think the highlights to extract from this are in red in the equation. Those are basically your environmental loads. It's your CO is the initial, like the background concentration of chlorides that are present as part of the mixing of the concrete initially. CS is your surface concentration, so what's like driving the chlorides in. T real is the annual temperature, so we were provided that information, and that's a direct input into the model. And then on the opposite side, on the resistance side, those are the green parameters. You have DRCM0, and that's what's called the chloride migration coefficient. And we saw in Neil's presentation, one of the input parameters that we were given was NT-Build 492 testing. That's actually pretty much the only input that we used from what Neil provided was that test data. And that's a test that's done at 28 days typically. It usually takes 1 day to complete, and can be done as part of, pre-qualification or even production testing. We have an aging exponent that was discussed a little bit before, and we'll talk more about that. And then, of course, you have your concrete cover, which is your kind of most significant, protection against corrosion initiation. Not going to go through this in detail. It's just to express the complexity of the input parameters. So these are describing all of the parameters that I just talked about. There's some short descriptions there. Fib Bulletin 34 does give recommendations on how to use those and what the values should be, or how to determine them. All of these input parameters are treated as distributions. So you see there, it's a normal distribution, deterministic value, log normal distribution, and that's how we're baking in the probabilistic side. Is actually all of our input parameters are distribution curves. And we'll see some of those later. And just following up, there's a few more input parameters. So not going to go through that in detail. This is basically from the fib Bulletin 34 extracted. And actually, I believe this table came from the Sharp 2 R19A summary guide. And that's available online for free. And essentially, this is kind of what we're modeling. So like I mentioned, all of the influential input parameters are probabilistic distributions. And this kind of cartoon illustrates the process. So up on top in the green, you have, let's take a step back. The vertical axis is your depth into the concrete, and then along the x-axis, you've got time. So your resistance is kind of indicated by the green, which is just essentially the depth of cover, and there's again a distribution of what that depth is. And then the blue is showing different curves of the depth of penetration over time of chlorides, and really it's showing the critical content of chloride, like how deep have you reached with a critical content of chloride that can initiate corrosion. And then what we're controlling is the overlap of those two curves, right? So that 10% that we talked about before, that's a sort of a 10% overlap, and then we stop. We talked earlier, there were some questions about limit states. So we have options for limit states, technically, for deterioration modeling. So there's an initiation phase where you're having chlorides penetrating into your concrete. You reach a critical value of chlorides, and then your corrosion can take off, right? Subsequent to that, you'll have corrosion products developing tensile strains inside of the concrete. You can start to see cracks, spalls, delamination spalls, and eventually collapse, right? Which all of that happens, hopefully years later. Typically, that's the case. So, but the assumption here is that depassivation, so just starting corrosion, that's our end of our service life. So it's very much a serviceability limit state. It's not an ultimate condition, right? As was discussed before, we have a 90% probability that corrosion will not initiate, or 10% probability that it will. And we'll talk a little bit more about reliability index, but this value beta, that 10% probability is roughly a 1.3 reliability index. So that's actually an input parameter into our model. Good. So we had to take a look at what we were asked to actually model. And there were three basic cases, right? We had the bridge deck, marine piles, and marine walls. And something we always have to do, and this was again discussed previously, is acknowledge the limitations and sort of fundamental assumptions of our model. So the fib Bulletin 34 model was rather developed considering concrete that's cast into formwork, right? So it's not developed or appropriate even for modeling concrete that's cast immediately against soil. The assumption was that these marine piles were cast against soil. And essentially, we wouldn't be able to apply the model in that case. Our actual design approach would be to rely on sort of deemed to satisfy provisions in that case, because the model is just not built for that, basically. So essentially, then we don't look at case 2. That's the last time we'll talk about case 2. And for case 3, it's assumed that marine wall is cast into formwork and then backfilled against, not cast sort of against soil. Good. Then we had our 3 mix designs. I won't dwell on this particularly long, but the important input here is we were using these chloride migration coefficient values for our modeling. So value 14 for the 100% cement, 3.6, marked improvement with the addition of silica fume, and then 9.6 with the HP20. I'll stick with HP as well. Then, what did we actually do? So, like I mentioned, we have this fib Bulletin probabilistic modeling. The brief here was to really look at these workshop input parameters, right? So, and I've put an asterisk there. We performed the modeling as requested, but acknowledging that certain inputs are sort of very not standard to the fib Bulletin 34. And so we wanted to see, well, what impact does that have? And this was already just asked earlier. So we looked at the default values too. So we've done parallel study. And then you see the dashed line, we bring in AASHTO Guide Spec as well, which hidden inside of AASHTO Guide Spec is a lot of fib Bulletin based modeling. So this is what it looks like then. We've got kind of boiled down to 2 cases, right? We've got our bridge deck with 2.5-inch cover, our marine wall with 3-inch cover, 3 different mix designs, and some key sort of differences here, right? So the workshop defined inputs, we're stopping hydration at 8 years. We're taking the H factor, and sorry, that's a little bit not the best color difference there, but I'll read it for you. H factor from test data, which is not per the fib Bulletin approach, so we'll talk about that a little bit later, but fib Bulletin gives a method to determine H factors. That's not this. But for the sake of this presentation, we've done as asked. And then we've used the C-crit, the critical chloride values provided. So we've got the black bar and this enhanced bar. We've needed to convert that to percent mass of cement. So that's our conversion, assuming a density, and we're given the concentration or the cement content in the mix design. So we've used that to get these values. In fib 34, H factor, as was discussed before, sort of on for the duration of 100-year service life. And then the C-crit values there, we used the default values, which actually are the same in the enhanced case, but for black bar, it's slightly higher. Again, we needed to do some interpretation of the actual results, of the input parameters to be able to run our model. In particular, we were provided a maximum surface concentration, but our model needs a mean. And we didn't want to set the mean to that maximum because then you're really skewing the exposure, right? You're really overemphasizing your load. So we made an assumption there, and you can see, so here we have probabilities plotted. So we treated the surface concentration as a log normal distribution. The curves that go up to 1 are the cumulative distributions, and what we said is like, well, this maximum value, we'll set that to a 95% on that curve, and then we sort of back calculated the mean in ppm, and then did a conversion, and I think that's on the next page here, did a conversion to get the mean surface concentration that we applied in our model. Again, these are percentage by mass of cementitious materials. So there's our mean value and our standard deviation. So a bit of analysis was needed to get a working input parameter there. Oh, and here you have the conversion assumptions there. So again, we were given the mixed design, so we know 658 is right, and then, well, pretty standard assumptions for the unit weight of the concrete to do that conversion. So again, like I mentioned before, this is one example of a distribution. This is how the majority of the input parameters sort of look in the modeling that we're doing. Okay, and then quickly we were provided this resistivity or bulk or conductivity testing at 28, 56, and 90 days. So we used that, plotted it, and extracted our H factors for the sort of first case calculations where we're using the workshop input parameters. So that's just to show the numbers. And as mentioned, we've done that for the sake of the conversation here, but it's not the right way according to fib Bulletin 34. Again, yeah, H factor, how the workshop approach, like we just showed how we got that. In the fib approach, you would either rely for your H factor on published results, or there are processes to determine an H factor, but the methodologies recommended take quite a bit more time than 90 days to extract it. So typically, in practice, we would be relying on published results. Good. So then this is sort of summarizing the H factors that were applied. So for the workshop approach, we have our values just from the figure a couple of slides ago. And then we've used, for fib Bulletin 34, published results. You'll notice that the cement and the silica fume mix, so control and SF8, use the same H factor, which is our typical approach with dealing with when dealing with silica fume. And then for the HP20, we applied, assumed that an H factor for Class F fly ash would be appropriate for that type of a material, considering it's complying with the same, actually, requirements. I mean, that material does comply with Class F requirements in the ASTM standard, and actually even better. So that was our sort of simplification here. Again, the input parameters for the different rebar types are here. The main difference to point out here is the black rebar with the workshop parameter is 0.4 mean. That was increased to 0.6 using the fib sort of default value. Enhanced rebar, for the workshop value, we just sort of created our A and B, the bound. So this is modeled as a beta distribution. So you have to have an upper and lower bound to bound that distribution. And it needs to be set carefully. So you have to really look at those distributions. So we made 0.9 and 2.9 based on looking at the actual distribution. On the sort of fib AASHTO threshold, we used parameters that are provided in AASHTO Guide Specification directly for the enhanced rebar. This is what they look like. That's the distributions. And there you see what I mean with the bounds. Like if you have too low of a bound, then the curve looks not right at all. So you have to be careful when playing with these input parameters and sort of really look at what you're doing. And the last input parameter is just the background concentration of chlorides. So with the sort of first case modeling, the workshop inputs, we use the value provided, which is actually quite low. In fib Bulletin 34, recommends a value of 0.1. So in our comparison, we have the lower value for the first sets of calcs and a little bit higher value for the second set of calcs. So what do we actually get? And what we're presenting here, so we've got our cases again. This plot should look somewhat familiar with our different, bridge deck, marine wall, different mix designs. And then what we've added there is T at beta of 1.3. That means the time when we sort of exceed the limit state, right? So we have a 10% risk of corrosion starting, and we're giving a bit of a time frame, bounding the time when we reach that condition. And I would say it's actually quite similar to what we just saw from the Life 365 model, that we're getting a 10% risk of corrosion initiation with the control mix around 5 to 10 years. The second column there is the reliability at 100 years. So how reliable is our design at the specified service life? Minus is bad. 0 is 50-50, right? Value of 1.3 is what we're looking for. And once you're getting to minus, you're having, greater risk that corrosion is starting than it's not starting. So it doesn't work, basically. And then let's do a quick comparison of the fib inputs. So again, keep staying with the control. We have time of beta same, still 5 to 10 years. The reliability index did get a little bit better, but it still doesn't work. One thing I forgot to mention back when I was showing the surface concentration, that's applied from day one in the fib. It's a simplified assumption, conservative assumption. There's no buildup of chlorides on the surface. So something else to consider, and probably part of the reason why the Life 365 modeling gave a little bit bigger, but I mean, at this point, it's basically I would say it confirms the Life 365 modeling that we saw earlier. Then if we start to walk down the figure, what we see is that addition of silica fume helps things a bit, but not enough to comply with the requirements. And then the helioclastite pozzolan further improves, but again doesn't get us all the way there. Kind of the big, something to point out here, if we look at the 3-inch cover thickness, with the workshop-defined input parameters, doesn't work. With the fib 34 parameters, it still doesn't work, but it gets pretty close. So, obviously when you're changing your input parameters, it changes the conclusions. We're going to take a step back in the conclusion slide and look at, does it work? Yes, no. And you'll see that it's quite uniform, actually, even with these differences in input parameters. Then we looked at the enhanced bar. The situation gets slightly better there. So the same exact figure, just results for the enhanced bar. So we've increased our critical threshold value. We need more chlorides to the depth of the reinforcement to cause a problem. Control still doesn't work in any case. The silica fume and the helioclastite pozzolan does work for both the 2.5-inch cover thickness and the 3-inch. Here you do see an example where the workshop-defined inputs are very close to working with the silica fume mix and then do work with the fib input parameters. Good. Then we had a look at this AASHTO Guide Specification. I don't have time to get into that in detail right now. That's the cover page. I think that's freely available, I'm pretty sure. And when you dig into it, there's a table that gives you cover thickness requirements. And here I'll read my notes again on this one. AASHTO Guide Specification for Service Life Design of Highway Bridges provides cover thickness requirements for concrete exposed to various environmental conditions, different service life categories. So you see down there at the end, there's normal, enhanced, and maximum. Enhanced is 100 years. It covers different reinforcement types. So you see reinforcement class A is black bar, B is something better than black bar, C is something even better, and D is stainless. So it doesn't exactly define what B and C are, but it gives you some variation. And B is the same, the 1.5% critical value that we see here. So B would be the enhanced. What else? In this example is showing one exposure class. So you see the CM3, which is the marine title. So this is what we looked at for the marine wall to extract information. So what does the AASHTO Guide Spec tell us? Essentially, similar, NA is not allowed, right? So black bar, control, mix, not allowed. in any case. Same with the silica fume. It's not allowed for any cases. What we could see for the sort of fly ash mix, the haloclastite pozzolan mix, it works, but you need to increase the cover a bit for both the marine wall and the cover with the black bar. And then it works, and actually you could reduce the cover a little bit when using the enhanced bar. So this is the sort of comparison table, right? So again, black bar, same kind of basic setup, right? We've got the black bar, the enhanced bar, workshop inputs, the fib Bulletin 34 default values, and then what does AASHTO have to say? And obviously when it's blacked out, it's not working. So with the workshop and the fib Bulletin 34 parameters, we're happy. We're smiling with the silica fume in the bridge deck. In the AASHTO, it doesn't work. And the reason for that is AASHTO covered 5 different mix design assumptions. So there was 100% Portland cement, there was a fly ash option, a slag option, and then fly ash and slag with silica fume. But it doesn't cover a silica fume mix by itself. So I had to sort of back down to assuming it's cement, actually. So it's indicative of the benefit of going deeper, right? So you've got a guide that is probably a bit more conservative, and it has an envelope, it's bounded by some assumptions that somebody made when they developed the standard. If you want to go and do a more refined analysis, then maybe you can improve and optimize a little bit and then allow a mixed design that wasn't allowed by the sort of, generic default background information. Again, with the pozzolan, if we increase cover a bit, AASHTO says it works. We didn't do those calcs to like increase the cover because we just explode our work if we went to find out how much cover do we need according to the calculations. But AASHTO gives an indication if you just increase cover slightly, then you have a working situation. And yeah, so here it speaks for itself. With the HP, I put a little kind of not quite so happy face because in theory that doesn't work, but we could probably do some minor modifications and get it working with the fib Bulletin input parameters. And I think that's basically it. So just to summarize and conclude, I mean, care is definitely needed, and you need to know your limitations of the available modeling. We talked about that with Life 365 as well. So you need to know the limitations, fundamental assumptions of the modeling tools used, and stick to that. Modify your default input parameters with caution. You really need to look at the distributions, make sure that they look reasonable, rational, not having tails cut off and so on. And I would recommend having sort of expert involvement once you're going beyond. There are kind of off-the-shelf tools available, like the AASHTO Guide Spec, where, if you're a structural engineer, you just can go into that and connect the dots and job done. If you want to get into the more extravagant methodologies, probably need to involve the right experts. And to conclude, I mean, we really found similar conclusions using the workshop input parameters and the fib ones in terms of, like, does it work or not? I mean, we saw the specific numbers change a bit, but can we apply it? Yes, no. Very similar conclusions. Maintaining aging of the chloride migration coefficient for the duration of the service life, of course, resulted in slight increases in the time when beta reaches 1.3 and the beta value seen at 100 years. And of course, use of rebar with enhanced corrosion resistance was effective and can permit use of concrete mix designs that wouldn't otherwise be allowed, according to the durability considerations. Use of calibrated deemed to satisfy method from AASHTO provides similar conclusions, but has some limitations and offers a solution avoiding improper use of input parameters, but with limited mix designs currently being considered. So I think if there's time.